Dear students, welcome to the theory session number 13 in the chapter of chemical bonding in physical chemistry. We were discussing about the molecular orbital theory and the molecular orbital diagram in our last theory session. Continuing our discussion, we shall be drawing the molecular orbital diagrams for a few more diatomic homonuclear molecules, and then we'll start drawing the molecular orbital diagrams for the diatomic heteronuclear molecules. First thing, we will try our hand at a few more molecules of AA type, that is the homonuclear diatomic molecule. We start our discussion now with lithium molecule. Now we have already written the electronic configuration for lithium. In drawing the homonuclear diatomic molecules MO diagrams, we shall concentrate ourselves only with the electrons which are present in the valence shell. The valence shell configuration of lithium atom is 2s1. Therefore we can say that the 2s orbital of one lithium atom can overlap with the 2s orbital of another lithium atom and will give rise to two molecular orbitals. We can name the two molecular orbitals. One will be sigma 2s bonding, another will be sigma 2s antibonding, represented by a asterisk or star. Now since the energy of the sigma bonding orbital is less than that of the sigma antibonding orbital, the true electrons present in the valence shell of the lithium molecule will occupy the sigma 2s bonding orbital and the sigma 2s antibonding molecular orbital. So this particular orbital will be vacant. So we can write the molecular configuration for lithium as sigma 2s bonding 2 and sigma star 2s antibonding 2. So this is the molecular orbital configuration for lithium molecule. Now if I draw the MO energy level diagram for lithium, it will be like this. So in the MO diagram, firstly, this is the area of increasing energy. Here we have the 2s orbital of lithium atom. So the 2s orbital So this is the energy level for the 2s orbital, and we can draw a dotted line demarking the separation from the atomic orbital. Similarly, there will be another 2s orbital of another lithium atom. So this is another 2s orbital of lithium atom. So this is one 2s orbital, this is one 2s orbital. So two particular molecular orbital will be formed. One is sigma bonding 2s, another is sigma antibonding 2s. Now since the sigma antibonding 2s is of a higher energy, it will be situated above. So here we get two molecular orbitals. One is sigma star 2s, which is the anti-bonding one, and one is sigma 2s bonding. In the 2s level of the atomic orbital of lithium, there were 1 electron each, and therefore there are two electrons to be arranged in the molecular orbital of Li2 molecule, and this 2 electron filling up will take place according to the Aufbau principle, the Hund's rule, and the Pauli's exclusion principle. And due to this reason, the 2 electrons are situated in the sigma 2s bonding molecular orbital. So this is the MO diagram for Li2 molecule. So this is the MO diagram. Now we move on to calculate the bond order, which we can easily do. That is the number of electrons in the bonding orbital, which is 2, minus number of electron in antibonding, which is 0, divided by 2, that is equal to 1. So bond order of Li2 molecule is 1. So I hope you have understood how to move on with drawing the diagrams for the molecular orbital for different homonuclear diatomic molecules. Now we shall be discussing a few more examples, and now we shall discuss the molecular orbital diagram for Be2 molecule. So we now discuss the MO diagram for Be2 molecule. Now the valence shell of of beryllium atom contains 2 electrons. That is, it has a configuration of 2s2. Now the 2s orbital of one beryllium atom then will overlap with the 2s orbital of the other beryllium atom and will give rise to 2 molecular orbitals. 2 molecular orbitals of the name sigma 2s bonding and sigma 2s antibonding. Now both of these molecular orbitals will be filled up with electrons, because there will be a total of 4 electrons that needed to be distributed. Thus we can say that the configuration for Be2 molecule this is a sigma bonding (2s), which has 2 electrons, and sigma anti-bonding 2s, which has also a total of 2 electrons. Hence the bond order for this Be2 molecule is equal to 0. Because there are also 2 number of electrons in the anti-bonding orbital, so this is equal to 0, and we can see that Be2 molecule does not exist. So if I am to draw the MO diagram, I can draw this as follows. So this is the energy that is going on increasing. So I have 2s orbital for one beryllium, So I have 2s orbital of another beryllium. So this will give rise to two particular molecular orbitals. One is sigma star 2s and one is a sigma bonding 2s. So one bonding and one anti-bonding orbital. The 2s level of beryllium atom contains 1 and 2 electron. So this will also contain 2 electron. So on a whole there are 4 electrons in the molecular orbitals that have to be distributed. So this distribution takes place according to the Aufbau principle, the Hund's rule for maximum multiplicity, and the Pauli's exclusion principle. So the 4 electrons are distributed as such: 1, 2, then 3 and 4. And obviously the bond order, which is equal to NB minus NA divided by 2, is equal to 2 minus 2 divided by 2, which is equal to 0. Therefore we can say that Be2 molecule does not exist. So the same kind of calculations can be both be obtained from the normal MO configuration that we have in case of the beryllium atom, and also by drawing the molecular orbitals diagrams. We now move on and try our hand at drawing the molecular orbital diagram for B2 molecule. Now in case of boron, the valence shell configuration (2s2), 2px1, 2py is 0, and 2pz 0. So there are a total of 4 orbitals. Now overlap of 4 atomic orbitals of one boron atom with identical 4 atomic orbitals of the other boron atom give rise to 8 molecular orbitals which are sigma 2s bonding, sigma 2s anti-bonding, then there is pi y bonding, then sigma x bonding, then you have pi y anti-bonding, pi z anti-bonding, and lastly you have the sigma x anti-bonding. So these are the 8 orbitals that are normally formed by the overlap of the 4 valence shell orbitals of the 2 boron atoms. Now we can draw the molecular orbital energy level diagram for B2 molecule. So we describe this as the molecular orbital energy level diagram for B2 molecule.